thanking Professor Ha for all this organization. And I also would like to say that I also want to thank Professor Kim, who I will visit next week. So I'm planning to tell you something about kinetic relations for compressible fluids. So at least I have fluid and kinetic in the title. That should fit this conference. And the basics, so let me start by showing you this class of system. So this is a class of systems of conservation laws. You can think of this part to be hyperbolic, or it could be hyperbolic elliptic. And I'm interested in the situation where you regularize the solution of that system by adding second order, third order, possibly even higher order terms. And what you are asking as a main question is, what happens when this parameter epsilon goes to 0? And specifically, what can be said about the limiting solution? So you expect them to be solution of the hyperbolic system, meaning that you can just drop this part and say that your limiting solution satisfies the system of conservation law in a weak sense, because typically u epsilon will be smooth, but u will be discontinuous. And then you want to know which weak solutions are selected by a specific mechanism. Right? So the typical mechanism would be to take only second order regularization here, and we know what we get. You know, we have to characterize a limiting solution by entropy conditions. There are many people, including Taiping in this room, who have been working on deriving entropy conditions when you make this regularization for your system of conservation laws. Okay? But what I want to do here is to tell you what happens if instead of this rather simple term, but still the theory of course is very complicated even with just that term, but still we want now to introduce higher order terms, so for instance 3 derivatives, and see what's going on in the limit. Okay, and there are many issues that come, but number of results have been obtained in recent years. So this is typically what we expect. We expect a competition between the regularization, which is induced by typically 2 derivatives. So this part will tell you that the shocks have to become somehow smooth, and by adding in addition a term containing 3 derivatives, what you observe are oscillations that enter in competition with the regularization. Okay? And these 2 effects, when epsilon goes to 0, somehow are gone, and when epsilon goes to 0, you end up with, say, a sharp discontinuity. But you want to know which discontinuities are selected by this mechanism. The motivation to do that is it really comes from the modeling of real complex flows, and typically flows involving phase transitions. There are still many more examples that I can be looked at, including, so more recently I've been interested in looking at the MHD, and we have seen the MHD model yesterday in one of the lectures. So with this magnetohydrodynamic model, you can include the so-called Hall effect that more or less correspond to this kind of effect of adding oscillation to the shocks. And again, these issues arises of what shocks are selected here. And again, we have seen yesterday that this is quite tricky. Okay, so there is a list of examples which probably I will not go through here. And what I will tell you is just a few things out of all these issues because of time constraint. So let's say roughly, let me go through this quickly. So the mathematical theory is based first on understanding the Riemann problem. And in this context, what we can construct is a so-called non-classical Riemann solution, which is defined not only using entropy or the usual entropy conditions that you are used to apply to systems of conservation laws, but in addition, there is something called a kinetic relation, a kinetic function, which somehow tells you among these non-classical shocks which of them are admissible, are physically selected by a given mechanism. So there is really this ingredient of a kinetic function that comes all the way, I mean, everywhere in the theory. You have to understand how it is used to solve the Riemann problem, then how it can be actually deduced from an analysis of traveling waves. And then this information of having a way to solve the Riemann problem in a non-classical way, this information can be used in a Gleam scheme. And so there are many things that have been done about that, of proving existence result for the initial value problem, and et cetera, et cetera. So there are all these mathematical issues where basically you produce a kinetic function and you understand how it comes from and how it can be used to solve the initial value problem, say at the hyperbolic or hyperbolic elliptic level of modeling. But somehow this theory has forgotten about these terms and only kept the information which is necessary to formulate a well-posed problem. Okay, then there is a second part where you actually want to compute these things, right? So you have to tell, given a kinetic function and given such a theory, how I am going to actually compute this solution by using a finite difference scheme. And there are a number of ideas that have been introduced here based on entropy conservative schemes, looking at the equivalent equations of the scheme to understand what is the effect of the diffusive dispersive terms somehow hidden in the scheme. And I've also been interested in actually computing the kinetic function. So there are cases where you can get them analytically, but there are very few cases where you can do that. So in general, the only thing you can do is compute these kinetic functions numerically, and that's interesting because it really allows you to make comparisons between schemes, between different models, etc. Okay, and so maybe for today, what I'm going to tell you is something about the derivation using traveling waves, right? And maybe not enter so much otherwise in the theory. And then, okay, then we will see, maybe I could also go into the third part here, where I try to actually analyze how far this theory is going, and there are actually some limitations. So if you have a system with two inflection points, so I'm going to tell you that one inflection point is really important to produce these new effects of these non-classical shocks. But if you have two inflection points, it's even more complicated. And there are some related issues about non-conservative systems, for instance. Okay, so let me jump over some of that, but okay, I guess not immediately. So let me show you the basic example, which Marshall, of course, knows very well. So he has pioneered this work on cell-similar solutions for the system of two equations of phase transitions. So typically, you should think of sigma to be non-monotone, in which case you have actually an elliptic region in your system of conservation law. And to that system, you're adding viscosity and capillarity. So there's these two terms, exactly the two terms I was talking about on the blackboard, except that now this is a 2x2 system, not, okay, I mean, or I could say that this is zero. I mean, you have zero in the first equation because this is somehow related to conservation of mass, and otherwise diffusive and dispersive terms in the second equation. Okay, so there has been a lot of work on that, and so the last three papers were precisely about deriving kinetic functions for that system and understanding how they could be used to solve the Riemann problem or to use them within a mathematical formulation with BV functions and solving the Cauchy problem. Okay, so that's a typical example you should keep in mind for all I'm going to tell you. And myself, I've been working on this subject with a number of people, so I put a number of names here, and I put also a number of names of people who have done related things in addition to the names I put on the previous slide, so including typing and many other people. So all of that is very much connected with these under-compressive shocks. So maybe I make another picture to tell you that the shocks that you know about have the properties that characteristics are impinging on the discontinuity, And the undercompressive shocks I'm talking about are shocks for which you have characteristics that go through. And so somehow they are less stable in a way, and they require additional admissibility condition to, to be well posed, to give you a well posed problem. Okay, so before I move on maybe a little bit quickly, let me show you the first pages of this section about the physical models. Okay, so I'm not going to enter into the details of these models, but at least I have to show you the scalar case. I guess, okay, sorry. Okay, so let me show you the scalar case. So the scalar case is simply taking a scalar conservation law and adding these two terms I was talking about before. And the observation that is made for this equation is that if you multiply this equation by u, you can, of course, produce a conservation form for the left-hand side, but not for the right-hand side. And in the right-hand side, you have left a quantity which is a dissipation that, in fact, only comes from this diffusive term. Okay? And the point is that the dispersive term here does not produce anything at this level and only enter in the second part, which is entirely conservative, in such a way that when you let, at least formally, but this can be justified rigorously, if you let beta and gamma goes to 0, what you end up with is an entropy inequality, meaning that this whole quantity here has to be negative, in a weak sense of distributions. So that's something that you want to keep, right? This is a nice information that you have an entropy inequality. Somehow this is, if you like, nothing new. But what is new is this last line that if you would try to do the same calculation with another entropy, it would not work. So there is really one specific convex entropy, u squared in this case, but it could be more complicated, which is associated with this specific regularization. Okay? So if I change that, I'm going to get another convex entropy here, and in general, there will be only one that you can use. Okay? So this is somehow the starting point.
I see. So,
if,
so
yeah.
in particular, if the small f is convex, then you don't get C nu.
Exactly. Exactly. I'm happy you see that typing. Good.
No, before I did not realize. This is, okay, that's good. I see.
Right. So this is really, I mean, and then maybe I'm not going to show you that, but if you solve the Riemann problem, the way to do it is to say, I do know that there is one entropy inequality satisfied. So you write one entropy inequality, the flux will be non-convex, and you try to solve with that, and you realize that it is not actually, one entropy inequality is not sufficiently discriminating to produce a unique solution, even at the level of the Riemann problem. Okay? And this is a beginning where you need to add this kinetic relation. Okay, so to continue with the story with the scalar case, of course it's natural to do that. You have two terms, two parameters. So I didn't tell you yet how these two parameters were connected, beta and gamma. And so these are the three regimes you can think of. Either this gamma you could think of being very small compared to beta squared. And in this case, the diffusion is dominant, and you don't need to take care of this gamma. Okay? The other regime is when the opposite, when gamma is dominant, bigger than beta squared. Of course, both of them are going to 0. So in a limit, really, they are gone. But in the second case, you cannot take a limit in a classical sense, in a weak sense, because of these oscillations. So what happens is that these oscillations will dominate in the second regime. They will dominate, and if you refine your mesh, for instance, if you compute that numerically, you will just see a train of oscillations that will not give you any strong limit. So the case I really want to study is this case where you keep the two effects in balance. And by doing that, you still have strong convergence. You keep these oscillations, but these are mild oscillations that are concentrated near the shock. So when you refine, when the parameter epsilon or whatever, beta, gamma, when they go to 0, what you see are spikes that concentrate near the shock. Okay? But away from the shock, these oscillations will disappear. And in addition, you do get shocks, but these shocks are not the shocks that you used to obtain by only adding diffusive terms. Okay? And this is the result. So these are oscillations that, again, will shrink to the shock location as you refine. And I show you two pictures where there is two shocks here, a pattern with two shocks, a pattern with one shock and one rarefaction. And these are, as you know, for a convex equation with a cubic flux. This would be impossible if you would be thinking of approximating this equation with only the diffusion. Okay? So there is definitely a new Riemann solver which is hidden behind that. And you cannot select these solutions by imposing the Olenek entropy inequalities or the Liu entropy condition for systems more generally. These conditions will not select what you actually want to select from a physical point of view. These are the correct solutions. So I want an entropy condition that produce these solutions. Okay? So I guess I have to be careful with the time, but we have a yeah. I normally have a small watch here. Okay, so we are fine with the time. So let me so let me skip these models. I mean, there are many models, but I don't want to talk about them now. So let me just conclude from this part that there are complex wave patterns. So you've only seen the scalar case, but believe me, for all the systems, it becomes more and more messy. It becomes more and more messy, and this is what we observe with the examples: complex wave patterns, different ratio, different regularizations, different schemes, numerical schemes, happen to produce different solutions, different shock wave solutions. Okay, so what I was describing here with this mechanism, you can change, you can make these terms nonlinear, there are parameters here that you can play with, and in the end you do get shocks, get somehow a nice Riemann solver if you are looking at the Riemann problem, but this Riemann solver depends on your regularization mechanism. And also, as Taiping pointed out, there is a single entropy inequality, and if it was convex, I guess this is what I put next here. So if it is convex, one entropy inequality is sufficient to produce uniqueness for Riemann problem and even more generally with these works. So this is really a situation where you can say that the shock wave solutions do not depend on the regularization, or at least they do not depend on the regularization as long as you have one entropy inequality. Right? So maybe your regularization could be even more crazy and not satisfy one entropy inequality, but this is not what happened in practice. You always have this single entropy inequality satisfied. And therefore, there is nothing new to be expected in this situation. Okay, so what do we need? So we need somehow to include effects that take place at the small scale level to see what the effect at the large scale. And what turns out is that the shocks that we produce will be called non-classical because they contain undercompressive shocks. So I wrote a picture on the blackboard to show you that. So these shocks are somehow less stable and they have so there is nothing universal that you should be looking for here, but somehow several series that you should be looking for. Okay, and it really depends on the regularization that you want to work with, and so I mean the idea I've been developing in the last 10 years or more is this idea of adding a kinetic relation to your system. Okay, so I will. Should I tell you? Okay, maybe let me. I guess I will try not to go into the technical details. So let me just say that the analysis to solve the Riemann problem is done by looking at the entropy dissipation function. Okay, so this quantity is what you get. I guess maybe I had it earlier. Okay, so I'm writing an entropy inequality. Okay, and to that I can associate this quantity. This is a jump of this measure on a discontinuity with constant state u minus u plus. This ratio here is the speed, of course, of propagation. And I'm just making some study of this quantity. And the only requirement I'm imposing is that this quantity should be negative for one specific entropy capital U. So if you look at this reformulation of the same quantity, you see immediately that if I was imposing that this quantity is negative for every capital U, every convex function, you could choose this U double prime to be arbitrarily positive, any positive function. Okay? And then you will end up with a statement about this quantity to be positive, to be negative, and there is a sign here. Okay? And of course, you recognize that to say that this has a sign is it should be the Olenek entropy condition. Okay? So this is not what I'm doing. What I'm doing is I have one specific entropy, and I'm only looking at this average. Okay, and so the result is like that this, for a specific fixed entropy, this entropy dissipation has this shape. It has a minimum at that point, which correspond to, maybe I could make a picture to illustrate that. So I have a picture of the flux. This is a flux of the function. This is f of u. And given any point u here, I'm defining this tangent point phi natural of u. Okay, and this is a point that you see in this picture here. So the sign of the entropy dissipation is correct up to this tangent point, but it is also correct for some additional interval until a point which I call the zero entropy dissipation function, where the entropy dissipation changes sign. Okay, so you have a whole interval here where you should not that you should not use normally to define shocks, but I'm still going to do that and introduce a shock that's jumped from u minus to a point in this interval here. Okay? So let me move on and show you the Riemann solvers that we end up with. So I guess it will be described as this picture here. Okay? So here you have the graph of the flux. And what I want to tell you is how do I solve the Riemann problem if you give me a left state which is positive here. Okay? So I have this left state positive. I want to solve the Riemann problem, but I am in a so-called non-classical situation. And this is a rule. The rule is that if the right state is bigger than UL, there is nothing new. Just use a rarefaction. Okay? Then if you are close to that point U left, nearby, you also nothing new, you use a classical shock. Okay? So the new feature will happen when you move away from that point U left, and you end up in this region here. Okay? And so to define this part, what I need to introduce is a so-called kinetic function that allows me to jump from this U left point here to its image. So there is a phi natural of U, which is, I guess this is called U flat or whatever. U, right? I guess this is U flat in English, right? You know music, yeah. You don't, okay. So no, I'm just confused right now, but no, I think it is, yeah. So this is flat, okay? So I'm jumping from this point U to some point phi flat of UL, okay? So that's what I will call the kinetic function, okay? So let me repeat. I impose a kinetic function, which is a function that for every U allows me to jump in this interval that starts from the phi natural of U over here to a point I didn't draw, but which is further down here, which corresponds to the zero entropy dissipation value here. Okay? So I have this rule that I can use this shock, and this shock is a non-classical shock. It is undercompressive. You can check that, because if you look at the tangents here, the tangent here will tell you what is the speed propagation, and you can see that the tangent at the point UL is it's bigger than the speed of propagation. And again, when you arrive on the other side, so here you have a UL value on one side and phi flat of UL on the other side. And and on that the other point, you see that the characteristics are faster. Okay, so this is what is given in this graph. And now I'm allowed to use this shock, okay? And this is something I call a non-classical shock under compressive. So how do I cover all these intervals? So there are basically two more intervals here I need to describe. So this interval n plus c means that you jump from UL to its image by a non-classical shock, and then you jump back by using a classical shock to cover this interval here. And the other possibility is, for the last interval, is to jump from UL to phi flat of UL, and then to follow the graph of the flux, and this corresponds to a rarefaction wave. Okay? So that's a picture, and of course you remember what I showed you numerically in the scalar case in the beginning, and you saw precisely that. You saw that there was a picture with two shocks, and I recover this two shock picture in this interval, or there was a picture with one shock and one rarefaction. Okay? So all of that is described by this. The only ingredient I need to describe this non-classical Riemann solver is this function here. Okay? So the claim I'm making here, I mean, from, say, a physical or numerical point of view, is that you can forget, at this level of description, you can forget about the regularization. You know, this complicated regularization, maybe discrete or continuous with parameters, etc. You can forget about that, provided you just keep in mind this kinetic function phi. Okay? So it contains all the information that you need to describe the dynamics of shocks that could be obtained in a limit. Now here you have some another pictures that actually show you this kinetic function for various regularization, various schemes, etc. So maybe I will return to that, but there are two boundaries here that correspond precisely to this natural function which is on the top and this zero dissipation function which is below, and there are various curves which I can obtain with various approximation mechanism. Okay. Okay, so let me move on. So this is just a summary of what you get, right? There are four cases: rarefaction, classical shock, or non-classical shock plus classical shock, or non-classical shock plus rarefaction wave. Okay, and here I just plot the two non-trivial cases. And of course, so you have to realize that these are shocks. I mean, there are no longer oscillations here. I had oscillations in the numerics, but in the limit, we just have constant state or smooth transition, but the hyperbolic theory does not contain any oscillations in it. Okay, so we have this result that if I have a kinetic function compatible with some entropy, then the Riemann problem admits a unique solution satisfying the conservation laws, the Riemann initial data, a single entropy inequality, and you can also check that there is this property of L1 continuous dependence, but this property is not, maybe it's not as nice as you would have in a classical situation because of this case, this situation. So you can very well, so if I draw the non-classical connection from, say, some state UL to phi flat of UL, you could think of taking a point here. So you could draw a situation where you put a left state here, and you take some u, maybe u is a parameter, and what I want to do is I want to take this value u to be either above or below this transition point. Okay, so maybe I didn't say that clearly, but this is a point I call phi sharp of UL. Okay, so I give the kinetic function, and then of course by just intersection with the flux, this point phi sharp is uniquely determined. And what I just want to tell you now is that if I take a u, which is either slightly, so this is a case where u will be slightly bigger than phi sharp of UL, and the other case, the other picture here would be a picture where I'm taking a u, so I guess it should be maybe slightly below compared to the previous picture. And so this is a case where this u now is less than phi sharp of UL. Okay? And so what you should observe is that there is a kind of spike because the two speeds of propagation can be very close to each other when you pass from a transition from a one-shock pattern to a two-shock pattern. Okay, so this is a source of a lot of difficulties at the theoretical level, also at the numerical level when you want actually to identify the non-classical shocks. This is some difficulty you have to play with. So I have another 10 minutes, Marshall, or something like that?
Precisely.
Okay. Okay, so let me continue with this. So there are generalization to systems, so let me jump over that. And so maybe I would be glad if I can tell you something about traveling waves here. Okay, so somehow what I told you is that if I have this kinetic function, I can solve the Riemann problem. And maybe you believe me that I can also develop the initial value problem theory, and things are quite well from that point of view. But now this ingredient of a kinetic function, I need to relate it to specific regularizations. Okay, so this is what this section is telling you, is how you actually find, sometimes analytically, sometimes explicitly, or at least you can show that such a kinetic function exists for a given regularization. Okay, so I cannot do that in general abstract regularizations, but I can do it for a number of examples. And here I would like to show it to you when you take a scalar equation and you add this nonlinear regularization for the viscosity plus a linear dispersive term. So F is assumed to be concave, convex, so the way, the shape I draw on the blackboard. And what I want to do here is do a traveling wave analysis to identify what are the correct shocks that are obtained. Okay? So this is what you do. You take your equation and you look for solutions that only depend on the parameter x minus lambda t. So you plot that in your PDE, and you get an ODE, which is nonlinear because of the flux and also because of this nonlinear diffusion that you have here. Okay. So look at this equation and impose boundary conditions at plus and minus infinity. Where you also, so of course you want the lambda to satisfy the Rankine-Hugoniot relation. I mean, this is something you can find out easily if you say you impose u prime and, you know, it has to go to 0, tends to 0 at infinity. So this is going to 0 at infinity. So this should be 0 and you find the jump condition. And I also should tell you that I've rescaled the parameter. So in this analysis, you don't need to introduce this epsilon. So somehow you are doing a blow-up of the shock structure, and that's what you want to do to get this kinetic function. Okay, so the question is whether we do get traveling waves that are classical or non-classical for this approximation. Is there indeed a kinetic function? Is it monotone? Because monotonicity, you show on the picture I show you, is actually a property that is usually found in the examples and needed for the theory. And another issue is the behavior when U is very small. So very small shocks, could you get non-classical shocks that are very small strengths? So we can actually answer all of these questions for that model. And earlier work was done by Michael Shearer, by Brian Hayes and myself, where we had other values of this parameter P. But the main difference, and also this was a cubic flux. So the main difference between this work and the work I'm telling you about is that here everything was explicit. So we can just found, I mean, look at this ODE and plug some expression, guess some expression of the ODE, and end up with an explicit or implicit expression for the kinetic function. Okay, so here it's more challenging because we actually need to prove that this kinetic function exists, but even though we don't have an explicit form for that. So the way to do it is to do a phase plane analysis in a U prime plane. Look at the equilibria. The equilibria turns out to be either saddle points where you have two real eigenvalues, opposite signs, or nodes, two eigenvalues with same sign, and you look for connections, right? So you have a dynamical, I mean, just a 2x2 system that you can write in these variables, and you look for connections, and there are two kinds of connections. So there are two kinds of connections. Maybe if I make another picture, basically, something similar to that. So the typical picture is that you fix a point u0, I guess. Okay, I'm not sure the notation I had here, but say u1, u2, okay, and you fix a u0. For instance, the way to do it is say u0 is fixed, and you also fix the speed of propagation. Okay, so for every u0, every slope, you get 2 points of intersections. You can think of u1 to be a function of u0 lambda and u2 the same. And you look for all possible connections that start from u0 and either reach your point u1. That would be a classical shock because you don't cross the flux of your equation, or your connection could go from u0 to u2, and that's a non-classical shock. Okay, so this is exactly what you want to understand. If you have a saddle node connection from u minus to u2, will be a classical shock. So I guess my notation should be a 2 here and a 1 here. And
Not quite a classical shock also. You'd have to stay on the monotone path. You couldn't have a shock into the spinodal region.
Okay, you have to be careful. The analogy with the system that you know is not quite correct, right? So you have to be a little bit careful. Right? So you have these two kinds of connections that you want to identify. So I guess in the last few minutes I can state that result, right? So the result is stated by defining this set. So I'm looking at all the states that from a point u minus. So now you think of your traveling wave, and you have a u minus that you have fixed, and you look for all possible states u plus, right? And you want to know what is the admissible Hugonot set corresponding to a point u minus. That's the question that we have here. And the answer is that we do get what we found by the previous analysis of the Riemann problem, which is that we found an interval plus an isolated point. And this interval and isolated point was determined by so-called kinetic function. Okay? So what I draw here, what I conclude here, is just what I already told you at the level of a Riemann problem. Okay? Except that now I'm finding this result not as some kind of assumption that I make by prescribing a kinetic function, but I find that by an analysis of traveling wave and the behavior of traveling waves. Okay? Okay, and then we have many more properties that we can derive about this kinetic function depending on various parameters. So you may remember that P was an exponent in a viscosity. So if you take a P to be large, it somehow means that you take this viscosity to be very small, right? In some sense, but in some sense. And this is what we recover here, because if P is large, indeed, we can prove that the kinetic function never coincides with the tangent function which corresponds to the classical construction. Okay? So that statement here is telling you that the kinetic function is always non-trivial. And in the opposite, when P is not too large, and in particular if P is 0, it means that we are looking at linear diffusion. In the linear diffusion case, for instance, there is a threshold, and the kinetic function coincides with the classical function if you are below some threshold. That is, small shocks will always be classical shocks in this regime. Okay, and we have some further information. Maybe let me not go into the details, but just emphasize that these informations are actually very useful in a BV existence theory for the initial value problem, because in that theory what you want to do is get a uniform BV bound, and the difficulty is about possibly having many non-classical shocks of arbitrary small strengths that would accumulate and might give you unbounded total variation. Okay, and to exclude this behavior, you need to have some information about the kinetic function for very small shocks, and this is precisely what I'm telling you here, because I'm looking at the kinetic function, the tangent of the kinetic function at the origin, and I can compare with various other values. Okay, so let me conclude with this. So maybe
In the scalar case, that's what.
Yeah, so this is, so far, this was a scalar case. Yeah. So let me just finish with this page here to tell you that both the Riemann problem and this traveling wave analysis have been done for systems to some extent, and specifically the 2x2 systems have been done. So starting with some work by Marshall Salembrode, more recent work by myself and Bejawi and Troskinovsky, Benzoni, Shearer, have allowed to understand the properties of traveling waves in a similar setup as what I've described. And even more recently, I've been looking at the case of van der Waals model, where you have two inflection points. Okay, so the equation of state would be typically the usual van der Waals shape, and maybe I could draw it here. I mean, there's just pressure, volume, so these are asymptotic to 0 here. There are two inflection points, and there are quite a number of interesting issues that maybe some of you would be interested to work on. Having two inflection points does not actually allow to treat the problem and to produce a Riemann solver based on a single kinetic function as I described here. Okay, so somehow the ideas I described do not fit completely well with this case of two inflection points, and we do get multiple Riemann solutions, so the story is much more complicated here. Thank you.